Let us now discuss an important property, that simple harmonic motion is the projection of the uniform circular motion along one of the diameter of the circle. Let us see an animation in order to understand this.
A very interesting point about a simple harmonic motion is that it can be considered as a projection of a uniform circular motion. That is, a uniform circular motion, when viewed sideways, is a simple harmonic motion. We can also consider a simple harmonic motion to be a shadow of a uniform circular motion. Let us say that the angular speed of a particle moving along a circular path of radius a is equal to omega. If the particle starts from this position, then after time t, its angular displacement will be equal to omega t, and this distance x will be equal to a sine omega t, which is in fact the equation of an SHM, as omega is a measure of the angular displacement per second. So omega can also be considered as the angular frequency in the context of an SHM. If instead of starting from this position, the particle starts from such a position, then the position of the particle after time t will be equal to a into sine of this angle, that is omega t plus phi. This angle represents the phase constant of a simple harmonic motion. When we say,
So from the animation we just saw that simple harmonic motion is nothing but the projection of the uniform circular motion along one of the diameter of the circle. That is, when a particle moves with uniform speed in a circle, itself the particle is describing the circular motion, uniform circular motion, but its shadow considered on any one of the diameter of the circle, that is along x-axis or along the y-axis, the shadow of the particle describes the simple harmonic motion. So that's why SHM is treated as a projection of uniform circular motion along one of the diameter. So in this figure you can see that we have a circle of radius a in which a body will be moving with the constant angular velocity omega. X dash and y dash, they are the two perpendicular diameters, two perpendicular axes for the circle. The circle in which body is moving, particle is moving, is called the circle of reference or reference circle. X dash is called a reference line. If the particle is to start its circular motion at the point A at time t equal to 0, we call this point as the reference point. So if the particle is moving with constant angular velocity omega, after time t seconds it will move from point A to B. So its position changes in time t from A to B, and its angular displacement, that is angle BOA, it will be equal to omega into t. Now if the particle is not starting its journey from point A, suppose at time t equal to 0, the particle is present at point A dash. So we have already called line XOX dash as the reference line. This means that the angular displacement of the particle, or the position of the particle at any time t, we have to measure as the angle described by the line joining the center of the circle O with its instantaneous position at time t equal to t with the reference line XOX dash. So when particle is already present at the point A dash at time t equal to 0, it has already displaced by a certain angle phi. So this angle A dash OA, which by which particle has already displaced from A to A dash, we call it as the initial phase of the particle, or it is also known by the name epoch. So at time t equal to t, the particle moves from point A dash to B. So it further describes an angular displacement omega t. Okay, so in this case, what will be the total angular displacement of the particle? It will be the total angle measured with respect to line xox dash, that is the angle the line OB makes with the x-axis. So that will be angle BOA, which will be equal to omega t plus phi. So the total phase or the total instantaneous position of the particle at the point B, it will be described by the phase angle omega t plus phi. In this omega t plus phi, which we have named as the total phase, consists of sum of the two terms, which one is omega t, we call it as the instantaneous phase, and the second term phi, which is called as the initial phase at time t equal to 0. So phi value signifies the position of the particle at time t equal to 0. So in the first figure, the particle already started its journey at the point A at time t equal to 0. So the value of the phi is equal to 0. So total phase over there is simply omega t. But if the particle is starting its journey from point A dash at time t equal to 0, so it has already described a certain angular displacement phi. In this case, this phi will not be equal to 0. So total angular displacement in time t from A dash to B, it is omega t, but we have to measure its total angular displacement from A to B, which will be equal to omega t plus phi. In order to find its instantaneous position of the particle describing SHM, we have to be careful about how its projection is moving along one of the diameter of the circle. So we take our reference diameter to be the xox dash. So when particle in anti-clockwise direction itself, it moves from point A to B along the circle, its projection, it will be moving along the xox dash axis from point A to towards the x dash. So in this case, when the particle is at point B, its projection will be present at the point M. So we drop a perpendicular from point B to M. So when particle's projection is point M, its instantaneous position from the center of the circle is x. So O is the mean position of the particle, A will be the extreme position along positive x-axis, and D will be the extreme position along negative x-axis. So in triangle OMP, the value of OM comes out to be equal to OB cos omega t. That is, x is equal to A cos omega t, where A is the radius of the circle. So omega t is the instantaneous phase of the particle. So in this case, the instantaneous position of the particle describing SHM along the xox dash axis is given by x is equal to A cos omega t. Remember, x is not the position of the particle which is moving along the circle, but x is the position of the projection of the particle which will be moving in along straight line from A to D and then back D to A. In this case, we have considered particle is starting from point A, initial phase is 0. But if we consider that initial phase is not 0, but it is present over there, then the total phase of the particle will be omega t plus phi. In that case, the equation of x will be x equal to A cos omega t plus phi. Velocity of the particle in simple harmonic motion. When a particle is describing uniform circular motion, its velocity is the tangential velocity at any point on the circle. We already know that tangential velocity is given by v is equal to r omega. R here is equal to radius of the circle, which is a. The velocity at any time t in simple harmonic motion can be obtained by having a time derivative of the instantaneous position of the projection of the particle. So if we take the time derivative of x, the velocity at any time t comes out to be minus omega a into sine of omega t plus phi. If we substitute omega a product equal to v velocity at any time t will be equal to minus v into sine of omega t plus phi, where we have used omega a is equal to v, which is the maximum velocity of the particle directed tangent to the circle at any time. Negative sign in this equation indicates that when the particle is describing its motion from point A to B, its projection is moving from x to x dash axis, that is towards a negative direction. So that's why negative sign is there. We can rewrite this equation in an alternate form. We know that sine square theta is equal to 1 minus cos square theta. So using this equation, we can write velocity at any time as minus omega a into square root of 1 minus cos square omega t plus phi. From this equation, if we get the value of cos omega t plus phi, it will be equal to x by a. So using that, in this equation, the value of velocity at any time comes out to be equal to minus omega into a square minus x square under the root. Now at mean position, when the particle is present, the value of x is equal to 0. So velocity is equal to negative of omega into a, which is the maximum velocity of the particle. Negative sign is only showing the direction that it is directed towards x to x dash axis. At extreme positions, when the particle is present, x will be equal to plus minus a. Plus a when it is moving towards the positive x-axis, and minus a when it is moving towards the negative x-axis, that is towards x dash. But in both the cases, the velocity at that point, it will be 0. So particle is instantaneously in the state of rest at the extreme position, because there it has to reverse its direction of motion. Last, acceleration of the particle. The acceleration of the particle is directed from its instantaneous position toward the center of the circle, that is, it is a centripetal acceleration, which can be obtained by having a time derivative of the velocity equation, which is minus v omega into cos of omega t plus phi. As v is equal to a omega, so we can also write acceleration as minus omega a square into cos of omega t plus phi. Now if with the value of the phi equal to 0, that is initial phase is substituted equal to 0, if we find the values of displacement, velocity and acceleration, so for different values of the instantaneous phase value omega t, if we find the value of displacement, velocity and acceleration and plot the respective graph, the graph will be as shown in the figure. So from the graph we observe that velocity is 0 when the displacement is largest, while acceleration possesses maximum value when velocity is 0. That is, velocity of particle is 0 at the extreme positions, but the acceleration of the particle is maximum at that point, because when particle is present at its extreme position, it is under maximum restoring force action, and the acceleration of the body is also maximum in value. Last, kinetic energy. We know that x is equal to cos of omega t plus phi, and velocity can be obtained from its time derivative, which will be minus omega a into sine of omega t plus phi. So kinetic energy will be half mv square, which will be equal to half m omega square a square sine square omega t plus phi. Using sine square theta plus cos square theta equal to 1 identity, This can be written as half m omega square a square into square root of 1 minus x square over a square, because as omega is under root k by m, so using that, half m omega square into square root of a square minus x square can be written as half k into square root of a square minus x square. Potential energy. Potential energy arises due to work done when body is moved against the restoring force present in the spring. Restoring force is minus kx. So if you want to displace the body by a distance dx against the restoring force, small work done for this will be minus f dx, which will be equal to kx dx with positive sign. Total work done for total displacement will be half kx square, which will be the potential energy of the body. Using the equation of x, this potential energy can also be written as half m omega square a square into cos square omega t plus phi. Then total energy of the particle will be kinetic energy plus potential energy, which is half k into a square minus x square plus half k s square, which will be E equal to half of k into a square. So we see that total energy of the particle always remains constant, independent of the position of the body within its two extreme positions. This is possible only if no frictional force is acting on the particle, describing the simple harmonic motion. Also, this can be expressed in form half m omega square a square or 2m into pi square f square a square, using the equation omega equal to 2 pi into the linear frequency f. The variation of kinetic energy and potential energy with the displacement and that of total energy is as shown in the graph. Last, we discuss simple pendulum. A point mass suspended by a flexible, inextensible, inelastic, weightless string, which is capable of describing a vertical circle. We call it as a simple pendulum. So in the figure you can see a heavy point mass m called bob is suspended from the rigid support point O with the ideal string of length L. When it is not undergoing any kind of motion, the weight is acting vertically downward direction and tension is opposite. Both are balancing each other. A reference line is passing through its center of gravity, which is the point A in the center, which is the mean position of the body. Suppose the bob of the pendulum is taken from point A to B. So it undergoes an angular displacement theta. When it reaches at the point B, tension in the thread is directed from B to O. Weight is still acting vertically downward direction. So in this case, angle AOB is theta. Then this angle will also be theta because it is a corresponding angle. So we can decompose the weight mg into two rectangular components. One component mg cos theta acting opposite to direction of the tension, balancing it, while the second component will be mg sin theta, which will be directed from point B to A. So when bob will be taken from A to B and it will be released, so it will be the mg sin theta component of the bob which will try to bring it back toward its mean position. So mg sin theta component will behave like a restoring force. So the restoring force acting on the bob will be minus mg sin theta. Minus sign we have taken over here because this restoring force is directed opposite to direction of displacement. So this angular displacement theta is increasing from A to B. Restoring force is directed from B to A. If the value of angular displacement is very small, then sin theta can be written equivalent to that of theta. Then restoring force will be minus mg into theta. If angular displacement theta is very small, then linear displacement from A to B, it will be x. Using definition of angle, length of arc over radius of arc, theta will be equal to x over L. Using this value of theta, restoring force become equal to minus mg over L into x. Using second law of motion, F is equal to ma. Comparing the two equations, value of a is equal to minus g over l into x. As g and l are constant, so a is proportional to negative of x. This shows that acceleration produced in the bob of the simple pendulum is directly proportional to its displacement with respect to the mean position a, but directed opposite to it. So motion is simple harmonic in nature. Now we have to find the time period. If we write the above equation, a equal to minus g by l into x only in magnitude form, and compare it with a equal to omega square x, we get that omega is equal to under root g by l. We know that time period is given by t equal to 2 pi by omega. If we substitute the value of omega here, the time period comes out to be 2 pi under root l by g, which is the expression for time period of simple pendulum only. Last, seconds pendulum. A pendulum which has a time period of 2 seconds is known as seconds pendulum. So if we substitute the value of time 2 seconds, acceleration due to gravity 9.8 meter per second square in above equation, and solve, the value of the length comes out to be 0.992 meter, or approximately 99 centimeters. So if we set the effective length of the pendulum, which is the length of the thread plus the radius of the bob, as about 99 centimeter, then this pendulum will describe its one oscillation in a time of 2 seconds. So hence it is known as the seconds pendulum.